In this video, we're going to go over how to do the magnetic flux equation. This equation looks like this. There's two ways to pronounce this letter over here, phi or phi. I pronounce it as phi, but you can say whatever you want. Ultimately, it doesn't matter.
Phi equals b times a times cosine theta.
Let's go over what each of these variables mean. This here, phi, this is the magnetic field passing through a surface. And this is measured in Webers, or WB. B is the strength of the magnetic field, and that's measured in Teslas. A is the area, and that's measured in meters squared. And lastly, we have cosine theta. Theta is the angle between the magnetic field and the normal, and that's obviously measured in degrees. Alright, let's go over what the angle between the magnetic field and the normal means. I'm going to draw out a surface, and in most cases, the surface is a floor. The normal is an imaginary line that is perpendicular to the surface. In other words, it forms a 90-degree angle. And this line over here represents the magnetic field. And the angle that we're interested in is this one right here. The angle between the perpendicular line and the field. It's very important that when you're looking for the angle, you don't use the one between the field and the surface. This is not theta. Now, there is one more thing I want to go over here. You've probably also seen the equation written out like this. Phi equals b times a, with no cosine theta right here. This is only true when the magnetic field is perpendicular to the surface, and we can visualize this quite easily. If our magnetic field came in perpendicular to the surface, this way, then the angle between the field and the normal would be 0 degrees. And when we have cosine 0, that really is just 1. So instead of multiplying cosine 0, we're really just multiplying 1 over here. And b times a times 1 is the same exact thing as just saying b times a. So when the problem tells you that the magnetic field is perpendicular to the surface, you would just use this equation. You don't have to worry about multiplying cosine theta. Alright, now that we got that out of the way, let's do some practice problems. A uniform magnetic field of magnitude 2 teslas passes through a flat surface with an area of 6.5 meters squared. The magnetic field makes a 35-degree angle with the normal to the surface. Find the magnetic flux. We're going to write out our equation. Phi equals b times a times cosine theta. As with everything you do, every equation, every formula, always write it out on the top. So we have our b, 2 teslas. We have our area, 6.5 meters squared, and we have our theta. If it helps you, we can draw a diagram right here. Here's our surface. This imaginary line is the normal, and this is our magnetic field. And that forms a 35-degree angle with the normal. Now we have to find the magnetic flux. We have our b, we have our area, and we have our theta. Let's just plug everything into the equation. Phi equals 2 teslas times 6.5 meters squared times cosine 35. We're going to plug this into our calculator, and we're going to get roughly 10.65 Webers. A uniform magnetic field of 0.5 teslas passes through a flat surface with an area of 2 meters squared. The field is perpendicular to the surface. The formula once again is phi equals b times a times cosine theta. But if you remember from earlier, if it's perpendicular to the surface, as it is here, we don't have to put cosine theta. So we would just write it as phi equals b times a. Phi equals 0.5 teslas times 2 meters squared. And you would just get 1.0 or 1 Webers. And just in case you wanted to plug in cosine, you would do so right here, and you would just say times cosine 0. And you would still get 1.0 Webers. Let's move on to the next one. A rectangular loop has an area of 2 meters squared. A 1.2 Tesla magnetic field runs parallel to the plane of the loop. Find the magnetic flux through the loop. So if this is our surface over here, and this is our normal, we're being told that the magnetic field runs parallel to the plane of the loop. So the magnetic field is over here, parallel to this line over here. Now, visually, we can see that if it's parallel to the loop, then it's not passing through it at all. So we know that the magnetic flux through the loop is going to be zero, because we can visually see that it's not passing through anything. But if you want to visualize this mathematically, the angle between the normal and the magnetic field is 90 degrees. So that's our theta. Let me just write out the equation over here. Here's our area, here's our B, and cosine theta. So when we plug it all in, and we're going to get 0, because cosine 90 is equal to 0. And it doesn't matter what this is, anything times 0 equals 0. So whenever you see that a field runs parallel to the plane or parallel to the surface, then we know that the magnetic flux is 0. Alright, let's move on. A rectangular loop has a width of 2 meters and a height of 1.5 meters. It sits in a uniform 1.2 Tesla magnetic field perpendicular to the loop. Once again, we're being told that it's perpendicular to the loop. So that means we could just say phi equals B times A. Here we have our B, but you'll notice that we don't have an A. We're given a width of 2 meters and a height of 1.5, but we're not given an area. Area equals length times width. We have a width and we have a height, which would be our length in this scenario. Let's just multiply it out. Area equals 2 meters times 1.5 meters, and what we're going to get is 3 meters squared. Alright, now we have our A. Let's find the magnetic flux now. Phi equals 1.2 Teslas times 3 meters squared. If you wanted to put the cosine, you would do so right here, but I'm not going to, because we know that cosine 0 equals 1. So 1.2 times 3 equals 3.6 Webers. Alright, I hope you guys learned something today. If you'd like to see some more complicated magnetic flux problems, let me know and I'll make another video. If you have any questions about anything I went over today, let me know down below and I'll try to answer you as soon as I can. As usual, thank you guys for watching and I'll see you in the next one.